So now we're going to go through an extended binomial distribution example. This question is actually taken from one of the books that we're in the midst of writing, but not finished yet. It'll probably be released sometime over the summer for, well, if you're in 1-2 at the time of upload, then it'll be useful for you guys going to 3-4 over the summer and throughout the year. Anyway, off topic. A fair coin is flipped 3 times. What is the probability of flipping tails on at least 2 out of 3 flips? Not on at least, on 2 out of 3 flips. So what we need to do in this case is first define our binomial distribution. So we can kind of see the variables here. So n is equal to 3 because we have 3 trials or 3 coin flips. And in this specific question, we want 2 out of 3 flips being tails. So we can consider tails as the successful outcome. So how we actually define a binomial distribution using kind of the official way is x squiggly line bi. So saying x is binomially distributed, and then the variables that we put in here are n and p. And that's enough information to define our binomial distribution problem. So in this case, n is 3, and a probability of success, if we focus on the tails, is going to be 1/2. That is really messy. Let me fix this up. I did not leave myself any space at all. But, okay, so 3 trials, and the probability of success, if we focus on the tails, because that's what's specified in this case, is going to be 1/2. I mean, it doesn't make a difference. If we focus on heads, it's going to be 1/2 as well, because they're the same probability. But now, cool. That's how we define our binomial distribution, and the reason why we do that is because if I just start doing things in terms of x, then the examiner is not going to know what the x actually represents. But now that I'm saying x is binomially distributed with 3 trials and a probability of success of 1/2, now I can use x freely in my calculations, and the examiner is not going to be confused. So now, if I actually want to calculate this probability, I can just say x is equal to 2, because I want 2 tail flips out of 3 trials. Then I just apply the binomial distribution formula. So go 3c2 multiplied by 1/2 to the power of 2 multiplied by 1/2 to the power of 1. Now 3c2, if I simplify that, it becomes 3 factorial over 2 factorial multiplied by 1 factorial. So the 3 factorial and 2 factorial would just reduce down to 3. And then 1/2 squared multiplied by 1/2 becomes 1/8. Therefore, we get 3/8 as our final answer. Now, you can see I did that pretty quickly in my head, 3c2. There's a couple of shortcuts that I've kind of figured out during my time teaching and also doing VCE methods myself. For example, if you have 3c2, I know that's going to equal 3. And for example, if you had 10c9, I know that's going to equal 10, because when you have just one less number on the bottom than you do on the top, it just ends up being the top number anyway. That's just something that I kind of figured as I was going. And also if you have, this is also going to be the same as 10c1. As well, and this is going to be the same as 3c1. So if you just have a 1 at the bottom as well, then you're just going to end up with the top number. So there's a couple of shortcuts that I figured out, and as you practice more and more, you'll figure out these things as well. Part B, what is the probability of flipping tails on at least 1 flip? So at least, so what are the different possible x values for at least 1 flip? You have x is equal to 1, so 1 tail, x is equal to 2, or x is equal to 3. So what we could do is calculate all these probabilities individually and then add them together. But that is very counterproductive. We don't want to do that. That's 3 different calculations like this, and then adding them together. It's going to take a long time, right? So what we do for at least 1 flip is we just do 1 minus the probability that x is equal to 0. And the reason why we can do that is because all of our possible outcomes will add up to 1, and x is equal to 0 is the only outcome that's not included in that set. So if you just go 1 minus the probability that's x is equal to 0, we're going to be left with x is equal to 1, x is equal to 2, and x is equal to 3. All those probabilities added together. So the fact that all of our probabilities add to 1 is a very useful tool using in binomial distributions. So I should specify this as x is greater or equal to 1, is equal to that, so 1 minus the probability that x is equal to 0. And you can always do this. If you have at least 1, you go 1 minus probability that x is equal to 0. That always works. For example, if you had x is greater or equal to 2, so at least 2 flips, let's say, then you go 1 minus the probability that x is equal to 0, minus the probability that x is equal to 1. So we're kind of like minusing all the ones that aren't included in that set from our total probability of 1. Hopefully that makes sense. And the good thing about this calculation as well is because you have x is equal to 0, it makes it really easy to reduce down. So what we do is 1 minus 3z0 multiplied with 1/2 to the power of 0, multiplied with 1/2 to the power of 3. 3c0, actually it just ends up becoming 1. So we've got 1 minus 1/2 cubed, that's 1/8. So we're left with 7/8 as our final answer. Okay, so here's part C. I just had to erase part A and B because it was getting a bit messy. But this type of question, before I read it, is a type of question that people don't like probability for. And the reason for that is because it's very wordy and it's almost comprehension that's difficult compared to the maths. So that's why a lot of people don't like these questions, because you have to interpret a lot of, mathematical things from this bunch of text. So we're going to try and break it down very slowly and figure out what's actually going on. Just as a reminder, x is binomially distributed with 3 trials and a probability of 1/2, and we're going to focus x on the tails, just to make it consistent. So we don't want to confuse the heads with the tails. What is the probability of flipping at least one tail? Okay, so we've got that part. What is the probability of flipping at least one tail? That's pretty self-explanatory, given that heads is flipped at least twice. So the reason why this question is confusing in terms of its wording is because it's referring to the tails in this part, but then in the second part of this sentence, they actually refer to the heads. So what we need to do is kind of make it consistent and focus on, let's say, the tails, because that's what we focused on previously. So if we want to write this in mathematical terms, what's the probability of flipping at least one tail? If we say x is tails, that's x is greater or equal to 1. But then we're given that heads is flipped at least twice. So if heads is flipped at least twice, what does that mean for our tails? So heads is equal to 2 or 3. There are 2 possible number of heads that we flip. So the corresponding tails for those outcomes are going to be 1 and 0. So what this actually means is, what's the probability of flipping at a tail at least once, given that tails is going to be flipped at most once? X is less than or equal to 1. So x is less than or equal to 1, or tails being flipped at most once, is the same as heads being flipped at least twice, if that makes sense, because they're just complements of each other. So now that we know this conditional probability expression, we can just use our conditional probability formula to simplify things. So we know that the numerator of our conditional probability is going to be the intersection between these two. And just looking at these inequalities, you can see the only overlap between both of them is just x is equal to 1. So this is going to be the probability that x is equal to 1 on the numerator. And then on the denominator, it's just going to be this expression here, which is probability that x is less than or equal to 1, which is the same as probability that x is equal to 0, plus the probability that x is equal to 1, because they're the only 2 combinations that are less than or equal to 1. Then I can just go ahead and evaluate this. So the probability that x is equal to 1, 3c1 multiplied with 1/2 to the power of 1, multiplied with 1/2 squared, and then the same thing is used there, but then we just have to add the probability that x is equal to 0. Quick shortcut, if x is equal to 0, we know that's the same as just flipping 3 heads in a row, which has 1 combination, so I already know that this is going to be 1/8 there. You can use a formula, but yeah, just a quick way of doing it. And then on the bottom there, x is equal to 1, it's going to be the same calculation as that. I already know 3c1 is going to be 3, and then 1/2 to the power of 1 multiplied by 1/2 to the power of 2, so it's just going to be 3 multiplied by 1/8, which is 3/8 there. So I'm just going to rewrite that more neatly. 3/8 over 1/8 plus 3/8. So we end up getting 3/8 divided by 4/8. And then the 8's cancel out, and you're left with 3/4 as your answer. Now, let's kind of think, how do I say? Conditional probability, it's kind of like an intuitive thing almost if you don't use the formula. So we can actually think about if 3/4 makes sense as an answer. What is the probability of flipping at least one tail, given that heads is flipped at least twice? So we can kind of think, if heads is flipped at least twice, what's the probability of flipping at least one tail? So we can look at our reduced formula and see that heads is flipped once is the only possible overlap between these 2 variables, and flipping a tail once is more probability than flipping a tail no times, if that makes sense. Hopefully that makes sense. It's making sense in my head. I'm just trying to I'm trying to think intuitively about it, but what I'm trying to get at is the probability that we flip no tails is only equal to 1/8. The probability that we flip one tails is more likely than that. That's 3/8. So the probability of flipping one tail is more likely than flipping the probability of no tail. Therefore, we expect this probability to be high. Yeah. Hopefully that makes sense to you. It doesn't matter if it doesn't make sense. I'm just trying to like think in my head. It's almost like a double check in my head to make sure that the numbers actually match up. But if you have faith in your calculations, then you don't need to do all this double checking. Sometimes I don't have faith in myself when I do the working out, so that's why I take this extra measure when double checking my answers.